as I said to the class some time ago, David is probably the applied mathematicians I admire more. His papers are a joy to read. And he will start now telling us about why it's important to do mathematical experiments in this new era. David.
Yeah. So let me try to do screen share. If it works.
Yep.
Okay. So I just have a few slides here, and let me first just make some general comments. The first comment is Tommy Poggio kind of got me interested in deep learning. He invited me to be a discussant at a conference that was going to be at Stanford. And, I hadn't really thought that much about deep learning until he enlisted me in that task. And then because I was doing that task, I got this request for a postdoc that happened to be from Vardan Papyan, literally like the same day or something. So I think I was in a math conference in Oberwolfach, Germany. And so I told Tommy, okay. And then Vardan asked, I said, well, I better, if I'm going to get it at all trying to understand things, I better get a postdoc involved.
Thank you, Tommy.
So these two guys are linked in my mind. And then there's a couple other links that I'll mention. So Vardan and I then the following fall at Stanford of 2017 taught a course, Stats 385, called Theories of Deep Learning. And it was the biggest PhD level enrollment I've ever had. Like well over 100 PhD students and maybe 200 in attendance. I've never seen anything like it. And Vardan was the person who knew a lot, and I was the person who was kind of learning something. And Tommy came and spoke. We had a bunch of theoreticians trying to tell us about theories of deep learning. And I have to say that Tommy's talk was by far the most successful. I mean, that's just objective, just from the feedback that we got, and you could tell it in the room and so on and so forth. His way of talking about problems and so on really made sense to a lot of people. What I observed from many of the other speakers is that they were, in a sense, from a different culture, and they were struggling to understand what's going on. Like, what is this new thing that's happening? And so I just thought I'd make a few comments and then hand things over to Vardan. So comment is about if we look at people who are interested in things that could be construed as data science. So I've stolen some slides from another talk here, and my apologies if there's irrelevancies on some of the slides. I just focus the things that are relevant to us. So people coming out of a mathematical theoretical tradition are pretty aware of this paper of Eugene Wigner, who was a Nobel Prize winning physicist at Princeton. And in this paper, Wigner says, look, math has been just crazy effective. And it's actually more effective than we can even imagine if we just sat down to think about what symbolic analysis of systems could do. And this was at a moment where in about 50 years, we had gone from kind of no space flight, no flight to flight, no understanding of, things like photoelectric effect to television and all kinds of radio communications and radar and stuff like this. And finally, from no understanding really of atomic structure in those 50 years to, quantum mechanics and everything that came afterwards, including nuclear power and, of course, nuclear warfare. So all of those things were on the backbone of mathematics because there were not really computational tools besides symbolic tools. And so the people who could do those things, like Wigner, were practically like a superior form of life or something compared to everybody else. And just, it was like magic what was happening in 50 years. And Wigner was writing at peak magic, let's put it that way. So, uh, and you know, things generally revert to the mean, and I think that's maybe what we're seeing now. Then in 2010, there's a famous paper by some researchers at Google saying, well, what's really unreasonably effective is data. And they were saying this in 2010. So I want, you know, then, you know, you could argue that as far as data, the world ain't seen nothing in 2010. The big revolution is what's happened in the 10 years since. Humans are posting 1 trillion images a year onto social media. Like, we have data that you couldn't dream of in 2010. Seriously. And, you know, their thesis has been proven out by, say, AlphaGo, and then the recent thing with AlphaFold and so on and so forth. What we understand is that getting data and holding challenges and pushing performance to win challenges is really revolutionary, and is maybe, who knows, the period from 2010 to 2060 might be as eventful as the period from 1910 to 1960 that we've just been mentioning in the paper at the top. However, many people who are theorists kind of don't or won't really understand the themes that are struck in this paper, Unreasonable Effectiveness of Data, and they're kind of stuck in the ideas of the unreasonable effectiveness of mathematics alone. I think it's important to have both in view. Okay. And we have to understand that there are these two cultures. And I would say the math culture really is something that we've seen since about the mid 17th century, growing and having, you know, really amazing impact on human development. But this sort of data first culture has been happening since the proliferation of computers, you know, through personal computers and the internet and things like that, which we can date like this. And all you know, the core concepts are really dual in every case. So we list some of them here, but I want to mention that people from the math first idea are thinking we need to have a generative model. We don't need data, we need a model that says data is just this stuff that's created by the model. And then we understand the model and we derive the consequences of it in some sort of analysis. And then we have understanding. And in the meantime, we actually never looked at any data whatever. We just did symbolic manipulations. And this is great for academia, and this is great for discourse between people who do such things. In the data first world, we're, you know, like, okay, we've got a new data source. We've got, you know, all the images posted to Facebook. That's a data source. We can make challenge problems, protein folding examples. And instead of deriving things, we build systems and we figure out how to scale them up to larger settings and things like that. We make measurements, and we don't really need to understand anything, but we do need to measure performance. This is all great for an industrial environment. It's great for producing products rather than discourse.
Excuse me, Prof. Donoho, are you changing your slides right now? I don't think we're seeing that.
You're not seeing the slides?
No,
I'm on a slide that says cultural differences. Is that not visible?
No,
no.
we are
Okay.
stuck at the first slide, the one
Oh,
on
I'm so
effective
sorry.
network.
Okay, so let me go back. I'll use a different screen share. I'll use just desktop. I was using the app. Okay, do you see something now?
Yeah.
Yeah.
Okay, so let me just go back. So I went through and just itemized the items in these two lists about it's a contrast between people coming from math and from the data world. And so in the teaching that Vardan and I did, we just found that the people who had, exceptional math training and were like this superior species of intellect in some way were really at sea facing what's been happening with deep learning, and they don't understand very well this data first world, which may be obvious to many of you, but we can't understand the talk that Vardan is about to give unless you understand this contrast. So I think everybody's seen this plot about the massive increase just in this decade.
Yeah.
And it's certainly continuing. There's no question. And because of that, this data first view has really taken over in this last decade. So what I'd like to emphasize is where a mathematician can, I think, contribute is to really understand that analysis, understanding, and discourse that are so central to the math way of looking at things have to change somehow. You have to operate in this other world where there's measurements, there's performance, and there's products. And in particular, the idea that you need models and derivations to get permission to do anything, that's very deep in a theorist's mind. Like, somehow your model's no good, you don't have permission to be doing what you're doing, is kind of very deeply embedded in all of these people who had to pass exams where if they did anything they didn't have permission to do, they would be failed. Whereas the people in the data first world is you just try stuff, and if it works, it works, and you don't need permission from anybody for anything. So operating in where can math contribute in all of this? I think the data first paradigm is kind of set. I don't see it changing. I would like to say that it's really in the place of understanding measurements right here. I have a pointer moving around the word measurement. I hope people can see that. And to underscore this, I think there's a blog post by Rich Sutton, who's a researcher in reinforcement learning that many people know, called The Bitter Lesson, which if you haven't read, you should read. And he essentially points to the idea that in every case where people tried to use theory to prescribe how to do things, it blocked progress. And the only things that have ever made progress are just general methods that use a lot of data and computation. And anyway, it's a point of view. And one of Tommy's colleagues at MIT, Rodney Brooks, has a counter post, which you might want to read, called A Better Lesson. So I'm not trying to advocate for this, but I think this is something that the gap that coming with preconceptions of a theoretical nature about how things ought to be done, that is what doesn't work. And it's a bitter lesson for people who have a strong intellectual preparation, say in the mathematical sciences, to understand that. So what does work probably is to look at these massive efforts. I mentioned AlphaGo, AlphaFold. Here's another one. In the class that Vardan and I co-taught, Vardan had Orhan Firat from Google AI come and discuss this model, which translates from any to any other of 105 languages, has 80 billion parameters, 25 billion examples. Because of the lesson on that previous slide, the bitter lesson, this is where we are. We don't try anymore to have simplified models based on theory. So what's left for theory then is to understand this, and I think focus on making measurements in this emergent field and discovering mathematical structures that are embedded deeply in these empirical systems that are being built. Now, it's a challenging interdisciplinary thing that I'm saying. So, for example, in some editorial roles that I have, I've seen papers rejected by people coming from the tradition in the left column who think if this is only true on these and these data sets, then it's not really true. It's only true if it's true symbolically in a generative model. That's the truth. The truth is not just some data you happen to get. Then it could only be on that one data set. Whereas if it were true symbolically, then it's really true. Okay, so there are ideas like that out there, and that's why perhaps this point of view is difficult for getting your papers published and for discussing with colleagues who don't really understand the right column. But I think there's a lot of opportunity to make measurements and discover the structure that's in them. And now, so Vardan was my postdoc at Stanford, and we co-taught these courses, and I learned a great deal from him. And now he's in the math department at University of Toronto. And we had a paper appear in Proceedings of the National Academy of Sciences recently, which I guess Tommy noticed or something. So he thought it would be good to have some presentation from us about this. And the details are going to be what they are, but this idea that math can contribute by making and explaining measurements is really what's exemplified in Vardan's talk. Okay, I'll stop sharing now.
Very good.
Okay, can you see my screen?
Yeah.
Okay, so hello everyone. Okay, so here's the paper, Prevalence of Neural Collapse During the Terminal Phase of Deep Learning Training, which appeared on PNAS on September 21st, 2020. The paper would not have been possible without these two individuals. XY Han, who's a PhD student in the Department of Operations and Research, I think it's pronounced, in Cornell, and Dave Donoho, who's a professor at Stanford, who we just heard. Part of the result that I'm going to discuss was a follow-up work that we're working on with Elon Kipnis, who's a postdoc at Stanford University. So deep nets represent a birth of a new field that has managed to lead to superhuman performance across many tasks. We've seen superhuman performance in image classification, in object detection, in natural language processing, in game playing, and recently in predicting protein folding. And so science today is fundamentally different in terms of what it can do with data. And there are certain distinctive features of this new regime, as Dave just told us, which are the prediction challenges are at the center of attention. And basically, if you are submitting any entry to those prediction contests, you can submit an entry which can be anything you want. There doesn't have to be any theoretical justification. And the prediction performance of your method is all that counts. Now, as a result, we've seen that the performance on benchmark datasets such as ImageNet has steadily dropped over the years and has reached the superhuman performance. Now, while all of this was happening, there were a bewildering variety of architectures that were developed, different tricks, different methods for training these huge, humongous models. And a person coming from theoretical statistics might think that all of these architectures have some type of peculiarities in them, and there couldn't possibly be some common thread that would be common to all of these winning architectures. But what we reveal today is that there is indeed a common outcome of DeepNet training. And this common outcome has, in fact, a very precise mathematical structure, and it has also theoretical explanations. By the way, if anyone wants to ask any questions, you can just interrupt me and ask me. So in today's deep learning, there is a reigning paradigm which says that networks are usually trained for, let's say, 300 epochs, a few hundred epochs. And the networks are extremely over-parameterized. We're talking about millions, hundreds of millions, billions of parameters. Now, as a result of this over-parameterization, the networks are able to reach zero misclassification error. And moreover, you can train them beyond zero misclassification error towards zero cross-entropy loss. Now, we call this phase of training beyond zero misclassification error towards zero cross-entropy loss the terminal phase of training, TPT in short. Now, let me introduce some standard terminology. So we're going to look at several data sets. Associated with each data set is the number of class, which shall be denoted by capital C. So for MNIST, CIFAR 10, etc., it would be 10 classes. For CIFAR 100, it would be 100 classes. For ImageNet, it would be 1,000 classes. Now, in each one of those classes, we have several observations, which we're denoting by XIC. So XIC is the ith example in the Cth class. So C goes from 1 to capital C, and I goes from 1 to the number of examples per class. Now, these observations are passed through the network, and we get a set of features in the different layers, which are the post-activations, post-ReLUs. And we will be talking for the most part about the last layer features, which are denoted by HIC. And these last layer features are multiplied by a set of classifiers, and then we get an estimated class C hat. Right? Now, all of these quantities depend on time or epoch, right? So the training error at time t would be the average number of errors that we have over the whole data set. So it's an average over some indicator, whereas the training loss at time t is the cross-entropy loss, which is the average of the minus log probability of the ith example in the Cth class belonging to class C. So I want to emphasize the distinction between zero error and zero, or the difference between error and loss. Now, in addition to the standard terminology, we would need some less than standard terminology, which is in fact standard in statistics. So we will be talking about the global mean. So the global mean is basically what you obtain if you take all the last layer activations and just average them. The class means is what you obtain if you take all the activations in a fixed class C and you average them. So you can think of it as the activation of an cat and the average activation of a cat in the last layer, for example. The within class covariance is a covariance which measures deviations of last layer activations from their true mean. And the between class covariance measures the covariance of the class means. Now, if anyone is uncomfortable with these definitions, we have an illustration. So today I'll be using this illustration quite a lot. So let me explain exactly what's happening here. So this is a sticks and balls plot where we consider there's various different spheres. Some are large, some are smaller, and different sticks, right? Now, the red spheres are the classifiers. So imagine if you have a set of classifiers, in this case, 3 classifiers, these are simply vectors, right, in some high dimensional space. So you can just plot the vectors, right, using a stick and a ball. And so you can see here 3 different vectors, and each is colored by a different shade of red. The shade represents the color. So we have the class 1 classifier, class 2 classifier, class 3 classifier. Next, we have the smaller spheres. So these small spheres represent the last layer features or activations, however you want to call them. So you can see the class 1 feature, the class 2 feature, the class 3 feature. Now, if you take all the features in a fixed class and you average them, you get the means, the class means. So here we can see the large blue balls are the feature class means. Okay. Now, what is the within class covariance? The within class covariance is simply measuring the deviations of the features, which are the small balls, from the means, which are the large balls. What is the between class covariance? The between class covariance is simply the covariance of these blue large spheres. And in it contains information about the geometric configuration of this class means. That's why it's a fundamental quantity. Okay, the last terminology that we need is what is a simplex equiangular tight frame, or simplex ETF in short. So a simplex equiangular tight frame is a set of vectors which satisfies 3 properties. The first property is equinormness. So equinormness means that you have a set of vectors. In this case, we have 3 vectors, which are colored in green, and all of them have equal norm, so equal length. The second property is equiangle. What is equiangleness? Equiangle means that if you take any pair of vectors and you look at the angle that they form, then the angle is always going to be equal, right? So you can see how the angle here is equal for any pair. And the last and third property is maximal angle. What does maximal angle mean? It means that not only are all of these angles equal, but they're in fact the largest possible equal angle you could get. It's essentially as close to orthogonality as you might get under the dimensions that we have. Okay, so with this terminology in mind, we're now ready to introduce what is neural collapse. Neural collapse is a set of properties, a set of properties that happen with the training of the network. And the properties are called NC1, NC2, NC3, NC4. So here I'm showing you what is NC1. NC1 is within class variability collapse, which basically means that the within class covariance is tending to 0. So here, hopefully you can see an animation. Does the animation move? Can you see a moving animation? You can. Okay, so what the animation shows is that the features, which are these small balls, are tending towards the class means as training progresses, right? And so this shows that the within class covariance shrinks to 0. Now this measurement is actually done on real data. So this is a VGG13 trained on CIFAR10. The next property is called NC2, and it is that the class means converge to a simplex ETF. So mathematically, you can define a simplex ETF as mu C prime inner product, once normalized by the length, is equal to 1 if C is equal to C prime, or equal to a fixed cosine, which is -1 over C minus 1. Right? So here you can see the two properties I mentioned earlier. So here you can see the equinormness, and you can see how there's equiangleness, and you can actually prove that this cosine is the maximal possible cosine. The third property is called NC3, and it is convergence to self-duality. So convergence to self-duality says that as training progresses, the class means and the classifiers are going to be equal. So the way you see it from the animation is the class means are the blue spheres, the large blue spheres. The classifiers are the large red spheres. And as training progresses, you can see how they align and become equal to each other. Now, in the previous slide, I forgot to mention that the way you can see the convergence to a simplex ETF is just by observing how the class means tend to the vertices of the simplex ETF, which are colored in green. So you see, as training progresses, the class means, which are the blue spheres, are tending to the vertices of the simplex ETF, which are the green spheres. So there's a fourth property, which is behavioral convergence to nearest class center. And what this property says is that as training proceeds, the decision of the classifier is just going to be equivalent to picking the class of the nearest class mean. So imagine you have a point in high dimensional space and you have a set of class means. The decision of the classifier is just equivalent to picking the closest class mean. The simplest possible classifier one could imagine. So what I'm going to show you now is evidence of neural collapse. And in each one of these slides, we're going to have in the rows a set of architectures in increasing complexity. So we have VGG, ResNet, and DenseNet of varying depths. And in each column, you can see a different data set, which is common or canonical rather in deep learning. So the first one is MNIST, the second is Fashion MNIST, then SVHN, CIFAR, CIFAR100, STL, and ImageNet. And these are again ordered so that you have this increasing complexity of the data sets as well. Now, in each one of the plots, the x-axis represents the epoch of training that goes from 0 to 350 for the most part. And you can see how there's this red line which appears in varying different places. This red line represents the point at which training has reached zero error, which means that every single point in the data set is being classified correctly. And what you can see is that training proceeds beyond zero error, right? Now, in this specific slide, on the y-axis, we're plotting how large is the within class covariance. And so the smaller the value, the smaller the within class covariance. And what you can observe in all plots is that as training progresses, the within class covariance diminishes towards 0. Now notice what's interesting is that in most plots, most of the decrease in the within class covariance actually happens in the terminal phase of training. That's where it truly becomes small. The next measurement shows you the standard deviation over the average of the norms of the classifiers of or class means. So basically, it's the coefficient of variation, as it's called in statistics, of the norms. And what this is supposed to convey is that the variation in the norms decreases with training. So all the vectors become of equal length.
Vardan?
Yes?
Excuse me, there's a question from a student. And
Okay.
she is asking if, when you say that the variance tends to 0, does it really mean that each activation really converges to the mean? Or is
Yes.
it somehow the sum over them?
No. Each and every activation converges to the mean. Thank you for the opportunity to clarify. Each and every activation. Do you remember how there was this visualization where you had these small balls that converge to the mean?
Yeah.
So that means that each and every one of them converges to the mean.
Then I have a second question. Have you verified that higher order correlations also disappear? Because I mean, if you're showing that the mean they converge in the sense that the covariance disappears, do like higher order moments disappear as well?
So you can just calculate the difference between the activation and the class mean, right?
Mm-hmm.
And basically, if the difference between the activation and the class mean becomes 0, then essentially everything has to become 0, right?
Okay.
So I don't think it's possible in this case. Yeah, because if the distance between two vectors is just 0, then I don't think the higher moments can.
I mean, maybe the question here is because you're plotting these things, and on the ImageNet, it seems like you're converging to some. If you go to the previous slide,
Yeah.
Especially in VGG, you see that it converges to something like order of 1. And
Yes. So basically, what this in the case of ImageNet, you can see a trend, and it's all a function of how much money do you burn. This is essentially. It's a question of how much do you do hyperparameter, how large is your architecture, and so on. If we had the budget of a gigantic high-tech company, I assure you we would get to 1e minus 4. It's just you need loads and loads of resources.
Okay, thank you.
Okay, so the second plot, as I mentioned, shows equinormness, that all the vectors become of equal length. The next measurement shows equiangularity. So this, on the y-axis, shows the standard deviation of cosines. So you have different vectors, right, which have a cosine, an angle between them. And what this measures is how does the standard deviation of the different angles look like as function of training. And you can see how the standard deviation decreases and becomes very small, which indicates that you have equal lengths and therefore equiangularity. And the next plot shows how the average angle approaches the optimal angle. So basically on the y-axis, you have the average angle minus what the angle should be for an ETF. And as you can see, the difference goes to 0. And so this means that if you combine these 3 slides, the first slide said equinormness, the second slide said equiangularity, and this slide shows that there's an optimal angle that you approach. If you combine all of these slides together, you get that the class means and the classifiers approach an equiangular tight frame. Okay, the next plot is very simple to explain. Here on the y-axis, we're just measuring the difference between the classifiers and the class means. And clearly you can see that the classifiers and the class means are very rapidly approaching each other and are in fact equal to one another. And the final plot compares the proportion of mismatch in terms of prediction of the classifier and the nearest class center algorithm. And you can see that as training proceeds, both of these decisions align with each other. So the classifier's decision is simply the nearest class center decision. Now, at this point, you might ask yourself, what is the significance of neural collapse? Well, the significance is that neural collapse happens simultaneously with improvements in test performance. So what this table shows you is the test accuracy at 0 epoch for the different data sets and network versus the test accuracy at the last epoch. And what you can see is that in many of the data sets, there's quite significant improvements. You see, for example, in ResNet, MNIST, you might say, oh, it's 99.3 versus 99.7, but that's in fact a very, very, very large amount of performance gain just by training beyond 0 error to 0 loss. Now, in order to explain the next benefit, I would like to remind you what is an adversarial example. So I believe you had a lecture by Professor Madri, is that correct? Who talked about this, but just in case anyone was missing from the lecture, I just have one slide to remind what an adversarial example is. So the idea is that you have an input to the network, which is a panda, and you can slightly perturb the panda by a tiny amount of noise to completely fool the network to think it's a gibbon. Now, optimization-wise, the way you do it is you look for a perturbation A that has a minimal norm subject to the constraint that the prediction of the XIC image after the perturbation is not equal to the original class C. Now, there's different ways to create such adversarial examples. And in our work, we utilize the method of deep fool. What a glorious name. And why am I talking about adversarial examples? Because as it turns out, as training proceeds beyond 0 error to 0 loss, and as neural collapse happens, one can observe improvement in the adversarial robustness of the network. So on the y-axis, I'm showing the perturbation required to fool a classifier, a network. The higher the perturbation, the more adversarial robustness one has. And as you can see, for almost all plots, with neural collapse, we get improved adversarial robustness. Now, it's important, for the most part, what we've talked about are the last layer features and classifiers. But one must remember that besides these last layer classifiers, which are just C-dimensional vectors, they're in fact a gigantic model which is creating the last layer features. And that model is parameterized by all the layers of the networks. And essentially, you can think of feature engineering as the act of optimizing the last layer features, right? And what we claim through this concise slogan is that neural collapse is the preferred end state of every successful exercise in feature engineering. So the fact that you see neural collapse indicates that feature engineering was successful. Now, one could ask themselves, why neural collapse? Why this set of phenomena? What's so special about equiangular tight frames? And in order to answer this, we need to go approximately 50 years ago to this seminal paper by Claude Shannon, which is talking about, it's titled The Probability of Error for Optimal Codes in a Gaussian Channel. So in that paper, what Shannon describes is the following thought experiment. Imagine that you have a certain transmitter who's transmitting a code word over a channel. The code word is picked uniformly from some code book. Now, this code word, which is transmitted over the channel, is corrupted by some type of a perturbation, which we assume is Gaussian. and then is received by a receiver. Now, the receiver is interested in decoding this message and understanding what was the original code word. Assume that this decoding is done using a linear decoder, which means with a set of weights and biases. So your gamma hat, which is the estimated code word, is simply the argmax of WCH plus BC. Now, what is the goal? The goal is to design the weights, the biases, as well as the code words, subject to a constraint of a norm on the code words, in order to get some type of optimality, right? Now, notice that this is, in some sense, analogous to what we have in the last layers, right? So the code words are the means. The Z, which is the noise, are the perturbations from the means. And the classifiers are just the weights, right? Now, in order to talk about, we say the goal is to design weights, biases, and code words, right? But in order to say how to design them, you must have an optimality criterion. So what we consider is a large deviation error exponent. So the large deviation error exponent is basically just the probability of a misclassification, the probability that gamma hat is not going to be equal to gamma. And this probability is taken as sigma goes to 0, as the variation goes to 0. And this is in fact correct in our setting, because in our setting, we know that sigma indeed goes to 0 due to the feature collapse. And so the goal of this exercise is to find what is the optimal large deviation exponent one could get. What is the optimal classification rate? And in our work, we show that the optimal error exponent is simply equal to C over C minus 1 multiplied by 1 over 4. But what's more important is that this optimal error exponent is in fact achieved by a simplex ETF. So what's the point? The point is that the simplex ETF is optimal under Gaussian noise. Okay, now you could envision a different scenario. Imagine that, again, we have a transmitter who's transmitting a code word over a channel, but this time, this code word undergoes an adversarial noise, which is bounded in L2 norm, right? So the receiver receives this message and again tries to decode it with a set of weights and biases. And the goal is again to design weights, biases, and code words. Now, in this case, we have a different optimality criterion. What is the optimality criterion in this case? The optimality criterion is we would like to have an optimal adversarial radius. So you would like to make it so that the adversarial noise that is required to cause a misclassification is as large as possible, right? So you want the configuration of the means and classifiers to be so that the adversarial perturbation required to fool the classifier is as large as possible. And as we show, the optimal adversarial radius is in fact achieved by a simplex ETF. So what does this mean? It means that the simplex ETF is optimal under adversarial noise. Now, what this theorem says at the bottom is that you can have a simplex ETF is basically defined up to a rotation on the left. So if you take a simplex ETF and you multiply it on the left by an orthogonal matrix, you just get a different simplex ETF. It doesn't change anything. So if we go back to our slogan, the slogan says neural collapse is the preferred end state of every successful exercise in feature engineering. The reason is because the simplex ETF is the unique optimal code that is optimal both in adversarial noise and Gaussian noise. Okay. So at this point, you might wonder to yourself, why do we get, what's the mechanism that causes neural collapse to appear, right? So in this part, I'm going to survey 3 works. The first work is by Webb and Lowe, the second is by Sudri et al., and the third is by Mixon et al. So the first work is by Webb and Lowe, who are prominent researchers in computer vision, and it's called the Optimized Internal Representations of Multi-Layer Classifier Networks Perform Nonlinear Discriminant Analysis. And what this paper says is basically that if you have a network where your criterion or your loss is mean squared error or MSE, and there's no feature engineering, then the optimal classifier and weights can be written in closed form. So the optimal classifier is equal to the pseudo inverse of sigma B plus sigma W, so the within class covariance plus the between class covariance multiplied by mu C minus mu G. Now, notice that this is interesting because it means that the classifier can be written in terms of the quantities we've spoke about at the beginning of the lecture in terms of the between class covariance and within class covariance, right? And what we show in our work is that if you add to their assumption, the assumption of NC1 plus NC2, meaning that you have feature collapse and that the class means converge to a simplex ETF, then you can actually prove that the optimal classifier weights are much more specific and they're simply equal to the simplex ETF. So we're essentially able to strengthen or boost the result and show that the optimal classifier of a network is in fact much more restricted than what they suggested. The next work that's related is by Daniel Sudri, Elad Hofer, Mor Spiegelman, Surya Gunaskar, and Nathan Srebro. I believe you've talked about this work in the class, right?
Yeah. Yeah.
And so in a nutshell, this talk is discussing an implicit bias of gradient descent on separable data. And in simple words, it says that logistic regression or multinomial logistic regression converges to a max margin classifier, and that there is an implicit bias of gradient descent that pushes logistic regression towards this max margin classifier. Now, if you look at their theorem says if you have a linearly separable data and you're using cross entropy loss, which is optimized with gradient descent with a small enough step size, then up to a scale, the classifier will tend to a solution of a C-class SVM problem, right? However, it turns out that if you add to their assumptions NC1 plus NC2, which means that the features are collapsing to their class means and the class means are the simplex ETF, then you can actually prove that the classifier weights are tending to a simplex ETF. So what this means is that the implicit bias in a deep network is much more constrained than the max margin implicit bias, because you're in fact tending to the most max margin classifier you might imagine. If you think about it, the neural collapse configuration is as optimal of a max margin as you might get, because everything collapses to a point and the class means are in a perfect max margin configuration. The last paper I'm going to talk about is a paper by Mixon et al. The paper appeared very recently. It's called Neural Collapse with Unconstrained Features. So if you read the paper, it says neural collapse is an emergent phenomenon in deep learning that was recently discovered by Han and Donoho. We propose a simple unconstrained feature model in which neural collapse also emerges. By studying this model, we provide some explanation for the emergence of neural collapse in terms of the landscape of empirical risk. Okay, so this paper by Mixon, Partial, and Pai is a brand new paper which appeared on arXiv just last week. And in the next few slides, I'm going to survey their claims. And I should mention that there may be details that either I haven't assimilated or they haven't explained. So the idea is as follows. Imagine that instead of looking at cross entropy loss, we just look at mean square error loss. And imagine that you assume that the last layer features are unconstrained by the previous layers. So they can just move freely, right? There is no constraint for the last layer features to be the output of this very complicated feature engineering pipeline. Then the MSC loss can be written as a sum from I to sample size of W multiplied by HIC, which is the feature, plus the bias minus the one hot target, which is EC. So EC is a vector with zeros and one at the Cth location. Now in matrix form, we can write this as W multiplied by H. So W is the classifier, H are the features arranged into a matrix, plus the bias multiplied by one transpose. So this is basically replicating the bias for all the examples, minus I chronicard one transpose. So I hope people know what a Kronecker product is. So basically, if you do identity Kronecker with a one's vector, it's just going to create different replications of the identity. How many replications? In this case, we have n replications. Why do we need n replications? Because we have n examples in each class. Okay. Now, in terms of dimensions, so W is a P by C matrix, where C is the number of classes and P is the number of features. And H is the matrix of all the possible features, right? So it's a matrix of size P times NC. P is the number of features, and NC is the number of examples in the whole data set. So you have n examples in C classes. Now, in their paper, Mixon et al. Defined the notion of strong neural collapse. What is strong neural collapse? Strong neural collapse is essentially equivalent to neural collapse, except they add two extra observations. The first observation is that the class means, are, so if you remember in neural collapse, we had self-duality, which said that the classifiers are proportional to the class means. But in strong neural collapse, Mixon et al. Say that the scalar of proportionality is in fact equal to 1 over square root of n. I feel like there is a question. Is there a question? Oh, it just turned your video. Okay, so the scaling between the class means and the classifiers is 1 over square root of n. And the second thing that strong neural collapse provides is an explicit form for the bias, which is just equal to a once vector divided by C. Okay, so what are these three properties? The first property, SNC1, is just saying that W, the gram of the classifiers, is equal to an identity minus a once vector. So this is equivalent to saying that the classifiers are a simplex equiangular tight frame. The second property, SNC2, contains in it both self-duality as well as feature collapse. So you can see here self-duality because it essentially says that the features and the classifiers are proportional to each other. And you can see here feature collapse because you can see how the features are independent of the different observations. So all the observations of the Cth class are equal to the Cth classifier up to a scalar. There is no within class variations. Now, because we have an MSC loss, and because we assume the features are unconstrained, then we can just optimize this loss using gradient flow for simplicity, right? So we can just write the gradient flow equations. So gradient flow just means that the derivative of h with respect to time, which is h prime, is just going in the direction of the derivative of the loss with respect to the features up to a minus sign. And w prime is just the derivative of the loss with respect to the classifiers multiplied by -1, etc. Now, notice here how there is a matrix A which is introduced. The matrix A is defined below. It's equal to WH plus B minus identity Kronecker ones. And in simple words, this matrix A is just the residual, right? It's just the residual, which is the difference between the prediction of the network and the actual target. Now, ultimately, with training, this residual would tend to 0. Unfortunately, this gradient flow is a nonlinear differential equation, and these are known to be notoriously hard. So what Mixon et al. Propose is a simplified differential equation. So they say the following. Imagine that I initialize my network near the origin. So W and H are very small. Then if W and H are individually very small, then the multiplication of W times H is also very small, right? And so what happens is that this term here, W multiplied by H in the definition of A, becomes negligible, and you just obtain this simpler matrix, which depends on the bias only. So they denote this matrix by M, right? So you get this simplified differential equation. H prime is equal to W transpose times M, W prime is equal to M times H transpose, etc. And this is a simplified dynamics which should hold, which is approximately equivalent to the previous dynamics around the origin. Now, why is this simplified dynamic useful? Because it turns out that you can prove the following result about this simplified dynamic. So you can show that the solution to the simplified dynamic satisfies the following inequality. So what does this complicated looking inequality say? It says something very simple. It says, if you take your tuple of features and classifiers at time t, up to rescaling, it's equal to the features and classifiers at initialization projected to a certain subspace. Now, the difference between the two is upper bounded by a term which is diminishing exponentially with time. So basically, it means that H and W, the features and the classifiers, are exponentially fast, converging to belonging to a subspace. I think that's an incorrect way to say it in English. Exponentially converging to belonging. Sounds a bit different. Okay, so what is this subspace T? The subspace T is the set of all tuples H and W which satisfy two properties. The first property is H is equal to 1 over square root of n, W Kronecker by 1. So that's basically one of the properties of strong neural collapse. And the second property is just that the global mean of the classifier is equal to 0. So again, I repeat, what does it mean for H to be equal to W Kronecker 1? It means that you have self-duality and collapse. So they're proving that you converge rapidly to self-duality and collapse. So I'm going to actually go over their argument in the next few slides. So the argument is as follows. For the bias, we have a differential equation, which is B prime is equal to this matrix M multiplied by the ones vector. Now, if you just plug in the definition of M, then you get that B prime is equal to N, which is a scalar, multiplied by the ones vector minus the number of classes multiplied by the bias. Now, this differential equation is separable in each one of the entries, and also it's not only separable, it's also linear. So linear and separable differential equations are easy, right? We can just solve it immediately. And you can see at the bottom of the page the solution. So for the bias, you have a closed form expression for the solution of the differential equation. Next, we move to the class means and classifiers. So here I'm showing you the simplified differential equation of the class means and classifiers. Now, what they show in the work is that this differential equation is defined through an operator L of t, which is a linear operator which depends on time and which is self-adjoint. Now, linear, you understand what it means, just linear. Time varying means that it changes with time. And self-adjoint means that if you were to form a matrix from this linear operator, the matrix would be symmetric. Now, what is the significance of the self-adjointness? The significance is that if a matrix is self-adjoint, then the eigenvectors corresponding to distinct eigenvalues are going to be orthogonal, right? Now, in their paper, they show that in fact, all of these matrices or all of these operators, LT, are simultaneously diagonalizable. What does it mean for them to be simultaneously diagonalizable? It means that all of these linear operators, which are self-adjoint, have the same eigenvectors, which don't depend on time. The only thing that depends on time are the eigenvalues, okay? Now, here I'm showing you the different eigenspaces that these operators have. And I gave them names which I think represent them well, and these names were not given in the original paper. So the first eigenspace is called the within-class variability eigenspace. And you can see that it consists of all the tuples HW, which satisfy the property I Kronecker 1 transpose H transpose is equal to 0. So what does this property mean? This property means that it consists of a set of features which within each class sum to 0. So you can think of this as the eigenspace of the perturbations from the class means, because the perturbations sum to 0. The next eigenspace is the set of all the features and classifiers which satisfy that the features are equal to W Kronecker product with 1. So this is the class mean eigenspace, I call it, because essentially in this eigenspace, the class means and the classifiers have to be equal, and also all the features have to be equal to each other within a class. Now, the reason there is a plus minus is because there is a positive eigenspace with a positive eigenvalue and a negative eigenspace with a negative eigenvalue. The last eigenspace is called the global mean eigenspace. So that's E2. E2 consists of all the tuples of features and classifiers where the features are equal to a rank 1 matrix Z1 transpose, and the classifiers are equal to a rank 1 matrix 1Z transpose. So you can think of Z as being the global mean, and essentially this eigenspace contains a rank 1 matrix corresponding to the global mean, okay? If you don't understand the intuition behind all the eigenspace, it doesn't actually matter for the proof. But intuitively, what this means is that if you take a set of features and classifiers and you project onto these eigenspaces, then the first eigenspace is going to capture the variabilities. The second eigenspace is going to capture the class means, and the third one is going to capture the global means. This is like a high-level description, which is completely imprecise, but this is my intuition. Now, why is this important? Why do we care about the eigenvalue decomposition? Because if you look at the differential equation is H prime W prime is a linear self-adjoint operator applied on H and W, which are the classifiers and features. Now, at this point, we know there's an eigenvalue decomposition of this operator, and so it can be written as a sum of projection matrices associated with the eigenvectors multiplied by the eigenvalues. Notice how the projection matrices don't have a time associated with them because they're fixed. All of these LT are diagonalizable in the same manner. The only thing that does change with time are the eigenvalues that multiply, right? For example, I'm 1 minus C beta. Now, why is all of this important? Because if you have a differential equation which is defined through a linear operator, which is simultaneously diagonalizable, it means that the differential equation can be written as a set of separate differential equations which are linear and independent. And so you can write this differential equation as these differential equations written at the bottom. Each one of those is very simple to solve because it's just a linear differential equation in certain eigenspace. And so here's the solution. So this is the solution to the differential equation in each eigenspace. And what you can see here is, let's say, for example, the last eigenspace, pi3, you can see that pi3 one is basically at time t is equal to the projection of the classifiers and the features onto this subspace at time 0. Because the eigenvalue is 0, that part of the solution does not change, if that makes sense. Now, notice how I highlighted here different quantities. And what they show, Mixon et al. In the work is that all of these quantities are upper bounded by some quantity exponent to the power of 2 over c squared of n. So this is just a very small exponent because n is very large, c is presumably large. And the proof basically concludes just by using the Pythagorean theorem, which is saying that the deviation between the features and the classifiers to the eigenspace pi1 can be upper bounded using this scalar e to the power of 2 over c square root of n times the energy in the rest of the eigenspaces. So hopefully this gives you some intuition for how to solve, formulate the argument. The argument is basically you have a differential equation. It is separable in each eigenspace. You solve each eigenspace, and then you just use Pythagorean theorem. Now, what's the bottom line? The bottom line is that gradient flow is initially pushing the solution of the differential equation consisting of the classifiers and the features to this very special subspace, right? The subspace consisting of features and classifiers that satisfy this equation here, right? Now, here we denote S as the 3-tuple of features, classifiers, and biases, right? Does anyone know what is missing from this argument at this point? Because this doesn't show neural collapse, right? What is missing here? So notice that this equation H equal to W Kronecker 1 is showing that the features are proportional to the classifiers. So that's showing self-duality. And it shows that the features are independent, or basically they're all equal within a class because they're just equal to the classifier, right? But at the moment, nothing says that the features and the classifiers tend to a simplex ETF, right? So that's the last part that's missing. And this is formulated in this theorem. So this theorem is showing the following. First of all, the subspace S, which is essentially the subspace of self-duality and feature collapse, is an invariant subspace of the differential equation, of the original differential equation, not the simplified one. What does this mean in human words? It means that if you have at some point, if you are in this subspace, and then you continue your differential equation, then you will forever be in this set, right? So this is what it means invariant subspace. It means that you keep on staying there if you reach that point at some point, right? And we know that rapidly in the beginning of the optimization, we're going to be approaching the subspace exponentially fast based on the previous theorem, right? So there is a good reason to believe why we would end up in this subspace. And what this is saying is that once you've reached this subspace, you continue remaining in it. The second part is the most important part, and it says that if you initialize your dynamics within this subspace S, then gradient flow will converge to strong neural collapse. So it will satisfy duality, it will satisfy feature collapse, and it will satisfy the property that you converge to a simplex ETF. So the argument for the first claim is just to show that if you have a point which belongs to the set S, then the gradient at that point also belongs to the set S. So I think I'm just going to skip it because I want to leave some time for questions. But I don't want to show this argument because this argument is very simple. So this shows why does a simplex ETF emerge. So the simplex ETF emerges by looking at the derivative of the gram of the weights with time. So define G to be the gram of the weights, which is just WW transpose. And let's look at this derivative with respect to time. So using the derivative of multiplication, you get that G prime is equal to W prime W plus WW prime. At this point, you can just plug in the derivative of the weights with respect to time. And the derivative depends only on the weights because of self-duality. So what you get is that G prime is equal to G minus G squared, okay? So this is the derivative of the gram with respect to time. Now, notice that if G prime is equal to G minus G squared, then this implies that the eigenvectors are fixed in the dynamics and that you have a set of differential equation in each eigenspace. So the differential equation in the ith eigenvalue is lambda I prime is equal to 2 lambda I multiplied by square root of n minus 2 lambda I. So if you just think about it, this differential equation has two possible outcomes. If you initialize it at 0, it will forever remain at 0. If you initialize it at a value greater than 0, you will just tend to square root of n. And so what does this mean? It means that as t goes to infinity, the spectrum, the eigenvalues of G, have c minus 1 eigenvalues which are equal to each other and one eigenvalue which is equal to 0. And this is literally the spectrum of a simplex ETF. So this proves that the classifiers tend to the simplex ETF. And the classifiers are equal to the features, and therefore the features are equal to the simplex ETF. So hopefully this made sense. So if you zoom out a bit from this mathematics, then essentially what Mixon, Partial, and Pi argue is that neural collapse happens if you have mean squared error loss, if you have gradient flow, which operates directly on the features and classifiers, and if you have this simplified initial dynamics, right? Now, in the neural collapse paper, what we showed was for cross entropy loss, neural collapse happens. And also it happens if you optimize all the layers of the network and you don't just, assume you can optimize the last layer features. And so this is a first step towards understanding the emergence of ETF, which, as we saw, has benefits for generalization and adversarial robustness. And we believe the next steps would be to make perhaps a similar understanding of the emergence of neural collapse under more realistic losses or more complex losses. And I believe Professor Poggio is working along these lines to show that neural collapse happens under, for example, exponential loss. So to conclude, we've seen that canonical deep nets and data sets show neural collapse. Neural collapse is extremely symmetric and simple, satisfying these 4 properties of no feature variability inside a class. The class means and classifiers are the simplex ETF, and the classifier decision is simply the nearest class center rule. We saw that neural collapse is optimal under adversarial noise and Gaussian noise, and it emerges in certain previous works, some of which were published less than a week ago. So thank you very much.
Well, thank you, Vardan. That's great.
There are some questions.
We have to finish the class at 12:25 now.
Oh, okay.
But students are free to leave, of course, to go to the next class. But let's, for the ones who can remain, let's, open the screen and the microphone to questions.
Okay, so there is already one question here that Tommy, you kind of alluded to. But Vardan, could you say something about how the results of the collapse say something about the generalization performance in deep networks?
Yes. the current work does not discuss generalization. So it could imply, I mean, I can make a simple argument, which is that a simple argument would say that, you know, by, I guess, law of large numbers or something like that, if your training data is large enough, then whatever you do in training would transfer to testing, right? And so, I mean, if you have a large amount of data, right? And so from that perspective, whatever we see on train should happen on test, just a little bit worse. So that's my answer at the moment. There's, at the moment, no better answer.
Maybe questions that you will have more answers about. Anyone else can ask questions, but I already have a few, so I'm just going to give a very quick one, just to clarify. And then I will let Leonard ask a question. But when you say that you have the simplex ETF solution,
yeah,
does that mean that the norms of each of them class means is the same?
Yes.
Is this equilateral, really?
Yeah, it does.
Okay, so this really means that the margins for every single data point on the whole data set is exactly the same.
That is exactly what it means. It's okay. A beautiful sentence you say, by the way, because what Andy is saying is that all the margins in the data set are equal, which is to be contrasted with what a max margin narrative would say, which is that there is a dominant margin. So thank you for that, Andy.
Very much opposed to the max margin solution.
Yes, thank you, Andy. Yes.
Okay. So maybe a related one. Do you see this for every network that you run, or is this? Are you selecting these plots? Are you finding?
I mean, I've showed the 7 networks, 7 data sets, and 3 architectures. It's 21 combinations. I feel like I've filled the screen with measurements.
Do they perform well? Is the question. Are they performing above chance?
We're optimizing the over like 25 learning rates in each one of the cases, and we compared to standard benchmark results, so they perform well above chance, I would say.
Now I'll open the questions to others, and maybe I can go back to mine.
Yeah, so it seems like Cynthia asked, may I ask a question about class variance tending to 0? Oh, so that was answered.
Yeah. No, but there is
Can I ask a question, please? Yeah. Thank you very much for your talk. It was very interesting, and I was wondering if neural collapse could have a link with double descent, deep double descent, and explain something there, because this could have a link.
Yes. Okay. Okay, here's going to be my answer. I would say if you go to the PNAS paper, there is a, you can click on the PNAS paper. There's a, I don't know how it's called, but basically in PNAS, they allow a person to write their opinion about the paper, if that makes sense. So Professor Miki Elad, who was my PhD advisor, wrote his opinion on the paper, and he discusses a bit the double descent there. But roughly speaking, I feel like this is a bit contentious, but roughly speaking, I would say the following. Double descent is a phenomenon that is usually defined on the y-axis. You have performance, right? Like misclassification. And on the x-axis, you have the size of the model, right? And so just by if you just look from this perspective, then it's different than double descent, because we're talking about dynamics with training, right? So from a first order point of view, it seems like there is no relation because we're having a different x-axis. If you look a bit more closely though, a relation could potentially be formed by looking at a paper, a recent paper that discusses a double descent phenomenon epoch-wise. Have you seen that paper?
Yeah, by OpenAI, deep double descent, right?
Yes. Yeah. So if you look at that paper, they suddenly talk about how there's a double descent phenomenon epoch-wise.
Yeah, this is what I was exactly referring to. This specific curve that where they show that it's occurring also.
Right. So what they show is essentially there is the second descent. Now, one could say that the second descent is happening simultaneously to neural collapse. So from that perspective, neural collapse would, in some sense, explain why does the generalization improve at that point. But
yeah,
I would
exactly.
like to,
This is what I was thinking.
So the co-author XY would make sure I mention the following. I don't want to piss him off. So in the double descent phenomenon that they talk about in this epoch-wise double descent paper, if you look closely at the experiments are being done with noisy labels, right? And so our work did not look at noisy labels. We always assume perfectly clean labels, right? And so I would caution about extrapolating between the two works, just because their phenomenon is on noisy labels, whereas our phenomenon is not on noisy labels. And in fact, as far as I understand, there's no double descent epoch-wise if you have no noisy labels. But you seem to be interested, and you're probably an expert on epoch-wise double descent. That's what I'm sensing from you. So maybe you know better than I do. Maybe you can tell me if
I don't know more. I just read this paper
Okay.
this morning. I reread it and thought it was maybe an
Okay.
explanation. And
Yeah.
there is this curve actually that with noisy labels, as you
Yeah.
say,
Yeah.
and there is another one where they don't mention noisy. They just compare with the width of the network.
Right.
But I'm not an expert, and I will look more into this and read the conversation. Thank you very
Yeah,
much.
if you look at the paper, I think you would find the answer to the paper interesting. Yeah. Thanks for the question.
So maybe just to follow up on that, is there the double descent is sort of related to like the over parameterization in with respect to the size of the, so for linear classifiers, it's the size of the feature space. So is one possible connection could be that maybe equiangular type frames are either easier to find in high dimensions, or they're high dimensional random initializations in those high dimensions are very close to equiangular type frames. So maybe that could be one possible relation over there.
Sounds like a good PhD work. Sounds like a good project.
Actually, that's a good question, because that relates to something else about that.
Yeah, it's a good question. I mean, I cannot answer from the top of my head. I can just say it sounds interesting. Yeah.
So I have a related, maybe not related, maybe related question, which is this. Especially for the second paper that you were mentioning, and the last paper that you were mentioning,
Mixon et al.
The MSE case. They showed that you can get basic neural collapse if you're assuming small norms.
Yes.
Now, and that somehow allowed you to linearize these differential equations and so on. Now, in the square loss case, the interesting thing is if you consider large norms, you end up getting in this neural tangent kernel regime where the dynamic seems to linearize, and you only have random features in the first few layers, and only really the thing that is interesting happens in the last layer. So somehow the opposite maybe of the regime in which you're talking about neural collapse. But then maybe the question is, that's about random Gaussian features or something like that.
Right.
That happens in there. Do you have any understanding of why somehow there would be this difference in no neural collapse happening for large initializations?
Why would there be no neural collapse happening for large initializations? I don't know from the top of my head, no. I can just say that in our work, our goal, right, is to look at what people are actually doing, right? When I say what people, if you remember what Dave said in the beginning, the point of this type of research is to make measurements of what people are actually training and to try to explain what's actually happening. And this kernel, neural tangent kernel, is in some sense not really what's happening in the networks people train, right?
I agree.
So all the
performance, but I'm just curious if there is this relation
Yeah, I agree. It's an interesting question. I don't know the answer though. It's an interesting question. Yes.
Vardan, just one curiosity, did you use batch normalization in your simulations?
Yes.
In all of
yes,
them? Okay.
Yes.
Yeah.
In all of them.
Yeah. Okay. And the other question is more general one, especially in the light of the Mixon paper.
Right.
What do you think your observations say about deep networks?
What do our observations say about deep networks? I think the observation is that people train beyond zero error to zero loss, and they observe that you get boosts in generalization performance and robustness. And neural collapse is happening simultaneously with that. So it explains that to a certain extent.
In some over parameterized regime.
Yeah.
I'm basically asking what are the key parts of Mixon et al. Model, right?
What are the key parts of Mixon? So the key assumption that they're making is the assumption that the last layer features can be directly optimized, right? So if you think about it in a network, there's no reason to believe the features can be an arbitrary vector, right? The features are the result of this machinery, which is very constrained in some sense, but in some sense not very constrained because you have so many parameters, right? And this part is completely missing from the unconstrained features model. Like, why are you entitled, for lack of a better word, to change the features as you please, right?
Yeah.
So that's the main modeling assumption in my perspective. Also, the MSC loss. Okay, so the main thing that they did was they proved that early on in the optimization, you converge to this subspace S of duality and collapse. But is that what we're seeing in the measurements? In the measurements, it seems like, I don't see that based on the measurements. I don't know, maybe you see it based on the measurements, but this is I'm unsure about that. Let's say it this way.
Sorry, what is...
So their observation is that if you initialize close to the origin, you're going to converge very rapidly to the subspace S, right? But who says that the feature collapse is happening rapidly and for the rest of training, you're just optimizing the angles? It could be that the feature collapse is happening gradually throughout optimization.
Yeah.
I think that's what we're seeing in the...
Yeah.
So I think there's a lot... Oh, sorry, go ahead.
Right, we have, prediction, at least for binary classification, because I was too lazy to do it to multi-class. But I think 4 property come out of a theory that tried to explain generalization. So,
with some caveat, tell me that I maybe want to talk to you about later.
Okay. But one key part is normalization of the weights.
Yeah, I saw that, yeah.
And so this is not required in terms of the algorithms if you use cross entropy, but it is if you use the square loss.
Yeah.
You need something like batch norm.
Yeah.
At least for my formulation.
Yeah. I saw that. Yeah. Yes.
Okay.
Tell me, it's Dave Donoho. I just sent you an email thanking you for the opportunity for us to speak and meet with your class, and then hoping that maybe Vardan and XY and I could have some kind of a Zoom with you next week to follow up.
That would be great. Yeah, that would be great. And thanks a lot for this. This was very, very good. Very, very interesting.
Thank you.
Thanks a lot.
Next week, can I challenge Vardan you to run these experiments on something that doesn't have batch norm?
Yeah, I can do that, yeah.
But I think it should work with cross entropy.
But I'm almost sure that it would work without batch. I'm trying to think if I ran it without batch norm.
The reason I'm saying, because in batch norm, you're subtracting the mean, so you're basically...
I know, yeah.
Mean. I'm not sure if this is something that you can derive without some kind of normalization like this that forces the means of activations.
Yeah, so Andy, I think it took me a while to understand why there's this mean subtraction.
Mm-hmm.
So what you might imagine, suppose I had three mean, I don't know if you can see my hands or not.
Yes.
But suppose I had three mean vectors in R3.
Mm-hmm.
You might think that orthogonality of those guys would be the right thing, right?
Yeah.
But what actually happens if you try to be optimal under either the adversarial noise or the Shannon model, is that those 3 points collapse down to R2, because in R2, they can actually be farther apart than orthogonal in R3. And that has nothing to do with any, so the thing that goes by pretty quickly in what Vardan was saying is that there's a negative inner product between every two vectors in one of these simplex ETFs. So they're actually farther apart than if they were simply orthogonal.
I see. Okay.
Which is like, so
if I draw three vectors on a plane, you're saying that the inner products are going to be zero.
Those three guys those three guys, if they have to be on the sphere,
okay, I see.
The orthogonal thing is not the best. They're actually going to collapse down and be like in the XY plane, and they're going to be more than orthogonal.
Mm-hmm. That makes sense.
So in some sense, do you have like an overcomplete dictionary?
Well, I mean, it's a very, very simple example of that. It's like the simplest possible.
Yeah.
Yeah.
We do like overcomplete dictionaries.
Yeah.
Yeah.
So Vardan and I both came out of the world of frames and tight frames and stuff. So I was worried at some point that this is all just being imposed by us.
Implicit
somehow. That's
bias.
why it's so important. Yeah, it's like I think it's really not. I think it's the strange Mercedes-Benz type structure has a fundamental nature to it.
Interesting. Well, very good. Thanks a lot, guys. David.
Okay, so we'll meet next week, I hope.
Yeah, we'll be in touch.
Okay.
And thanks to all.
Thank you. Bye-bye.
Tommy, do you have time to chat about this actually?
Yeah.
Because I've been actually, I was working on this the last few days.
Okay.
This talk exactly like got me, so I got to this conclusion that I had to ask this question. Basically, all the points in this neural collapse are the same margin. And the same margin. I mean, all of the data points have exactly the same margin. This is not entirely compatible with what we've been doing. Or more precisely, like if you think about the theory we've been building, this says that we have no way of distinguishing the different points. So the margin distribution is flat.
Yeah, but no, I say this in memo.
So I agree that probably happens. But the arguments we've been trying to build with saying, smaller number of support vectors leads to better generalization.
No, but okay, in the square loss case, that's exactly what I'm saying. If there are different minimizers of the square loss, and if you assume exact minimization, absolutely zero error, then for each of these minima, you have that the margin for a point is inversely proportional to rho, and is the same for every point.
Yeah.
If you want to.
I think, yeah, I also observed that in the paper that the margin seems to be the same for every point.
If you have zero, exactly zero square loss, and if you look at the plot that we have, it's almost flat. You know, there is a little bit of sigmoids at the two ends. So there are a few points that are, but look at the scale, there's very small number.
No, so this definitely agrees with the experimental verification of what Fernanda has been doing with checking that you get better generalization performance if the whole distribution of margins is lower or higher. I think this is consistent with this.
Yeah.
But I just want to see this derivation that is right now in the appendix, in which you show the binary case, that doesn't entirely follow through. And the reason it doesn't is currently that equation 44 that is in the appendix, in which you have VFC being dFC by dV.
Yeah.
That we have that equation as a sum over classes. We don't have that equation as per each class.
But somewhere else I say if this equation 44 at this global minima has to be valid for each of the data.
Yeah, so if we somehow manage to get equation for derive it, I don't think we have derived it. But I agree that equation 44 implies neural collapse if you converge to it. But I don't think we have shown that from our analysis yet. I feel like that's the kind of missing step to show that per class.
Converges?
I don't think we have shown that per class this is satisfied.
That per class?
We have shown that the sum over examples and weighted sum over this is true. And this is
okay. Somewhere else in the memo, I wrote something that at the very close to the minima, it has to be true for each one of the training examples, not just for the average.
Mm-hmm. I mean, it's not in the case of what we've been getting for the equation for V and well, F and dF by dV. That was like an equation that is using this weighted, exponentials or up or error.
Right. What I'm saying that is
at the global minimum, where you're saying that the loss is zero, and for saying all of the.
If you look at Appendix H, I'm saying that this equation is true for each one of the examples.
H.
Yeah.
That's the one where you're, but you're okay.
Right. They say somewhere else that maybe not in the version you have. But...
Okay, yeah. I see.
No, I think one thing is missing is a proof that has to be for gradient descent, not gradient flow. So that's something I don't have, is that you have convergence to the best minimum. Because this will depend on having the correct learning rate and so on for gradient descent. You know, it seems reasonable that you converge if you start from zero, you converge to the global interpolating solution with minimal rho, the smallest rho. But
the question is, I mean, based on these experiments that he's been showing, it seems like we seem to be converging always to the solution that has all of the margins being the same. I'm just saying, if we assume something in our analysis that all the margins are the same, so many things simplify. We can prove so many of these results.
Well, wait. The idea is that there's more than one solution, and exactly the solution, the margins are all the same, but for this different solution have different margins.
Yes, I agree.
And I think each one will probably show neural collapse.
Perhaps, yes. I
don't think neural collapse will choose a better.
I completely agree. If we have multiple solutions that have all the margins the same, they will be max margin solutions, and they're going to have all the properties.
Yeah.
Because you're going to converge to something that is NC1,